Bell-shaped histograms. Many histograms have a single mode near the center of the data and are approximately symmetric. Such histograms are often referred to as bell-shaped. So here you can see clearly the bell shape of the histogram. The empirical rule. When a data set has a bell-shaped histogram, it's often possible to use the standard deviation to provide an approximate description of the data using a well-known rule as the empirical rule. This is one of two that we're going to look at. Approximately 68% of the data will be within one standard deviation of the mean. So as you notice, you've got the mean minus one standard deviation, the mean plus one standard deviation, and the mean is right in the middle. Approximately 95% of the data will be within two standard deviations. So again, from here, minus two standard deviations plus two standard deviations, or almost all of the data will be within three standard deviations. So from here to here. Almost all is approximately 99.7%, but for this section they use the terminology almost all. As an example of the empirical rule, the following table presents the U.S. Census Bureau projection for the percentage of population age 65 and over for each state and the District of Columbia. Use the empirical rule to describe the data. So first thing you do is you know that the histogram is approximately bell-shaped, so we may use the empirical rule. For your problems in the homework, you're not going to have to gather the data and make the histogram to determine this. They're going to tell you that it's a bell-shaped curve, and you automatically go to the information. So this information down here will be given to you. So the mean is 13.5, and the standard deviation is 1.683. So to calculate the mean, all they did was add them all up and divide by how many there were. And to calculate the standard deviation, they went through that formula x minus the mean squared divided by how many there are. But they came up with these two numbers, 13.25 and 1.683. So let's use this data and see how it fits in the empirical rule. Notice they're taking the mean minus the standard deviation, the mean plus the standard deviation. That was this right here. This is the mean minus the standard deviation. This is the mean plus the standard deviation. So if you look up here, the mean minus, so 13.2, that was the mean. Subtract the standard deviation, you get 11.57. The mean plus, you get 14.93. So 68% of the data falls within this range. Then you do twice that. So the mean minus twice, the mean plus twice. So you do 2 times 1.687, and then subtract that from 13.289, and then 13.249 plus twice. So you get the numbers 9.88 and 16.11. That goes here. And that means 95% of the data is within that range. And then you add and subtract 3 standard deviations, and you get 8.2 and 18.3. So almost all of the data, or 99.7% of the data, will be within 3 standard deviations. So let's just try another one. Let's say I have some data and I know that the mean is equal to 2.793 and the standard deviation is equal to 0.25, let's say. So I want to make my empirical rule chart. So I make my little thing and I put the mean right in the middle, 2.793, and now I want to go out 1 standard deviation, so I'm going to go 2.793 minus 0.25 and 2.793 plus 0.25. So let's clear this out. So 2.793 minus 0.25. So I get 2.543. And then I do 2.793 plus 0.25. That gives me 3.043. So I could put those two numbers here. So this is the minus one, 2.543. This is 3.043. Now I want to go out one more. So I do 2.793 minus twice the standard deviation, 2.793 plus twice the standard deviation. So on my calculator, I can do 2.793 minus 2 times 0.25. I get 2.293. Make sure you're trying this on your calculator and you're getting the same numbers as me. 2.793 plus twice standard deviation, and I get 3.293. All right, so that goes here. 3.293 and 2.293. Finally, 3 standard deviations out. It's going to be 2.793 minus 3 times the standard deviation and 2.793 plus 3 times the standard deviation. So 2.793 minus 3 times 0.25, 2.043. And then I do 2.793 plus 3 times 0.25. So I'm just using decimal numbers so you can see that you can do this also with decimal numbers. That was 3.543. So here is 3.543, and this is 2.043. So 68% of the data is within the first standard deviations. And notice how it looks the same way. So 68%, 95%, almost all, or 99.7% of the data is within that range. When a distribution is bell-shaped, we use the empirical rule to approximate the proportion of data within 1 or 2 standard deviations. Another rule, called Chebychev's inequality, holds for any data set. Notice this does not follow in the bell curve. That's why you can use this one now. In any data set, the proportion of the data that is within k standard deviations of the mean is at 1 minus 1 over k squared. Specifically, by setting k equal 2 and 3, we can obtain the following results. At least 3/4 or 75% of the data are within 2 standard deviations, and at least 8/9 or 89% of the data are within 3 standard deviations. So let's just look at this for 1 second. They're saying 75% within 2 standard deviations. So on the bell-shaped curve, here was our 2 standard deviations, right? 2 away. You're at 95%. Quite a difference. So we only have 75%, 2 standard deviations away. 3 standard deviations away, right here, it's at 89%. And on a bell-shaped curve, 3 standard deviations was here to here. It was almost all of the data, or 99.7. So again, there's a little bit of a difference, but these are for non-bell-shaped curves. So how did I get this 75%? Well, 75 is when k is a 2, 89 is when k is a 3. So when it's a 2, all they're doing mathematically is saying 1 minus 1 over 2 squared, right? K squared. So this is 1 minus 1 over 4. So 1 minus a fourth, or 4/4 minus a fourth, is 3/4, and 3 divided by 4 is 75%. So on a calculator, if you were to look at that, 3 divided by 4, you get 0.75, but then to convert that to a percent, you multiply it by 100, and you get 75%. Now when k is a 3, it would be 1 minus 1 over 3 squared, so that's 1 minus 1/9, and converting 1 to ninths, 9 over 9 is a 1, minus 1/9, 9 take away 1, so that's 8/9. So when you divide 8 by 9, you get approximately 89%. So that's where they're coming up with those numbers. Here's an example. As part of a public health study, systolic blood pressure was measured for a large group of people. The mean was 120 and the standard deviation was 10. What information does Chebychev's inequality provide about this data? So we know two things. The mean is 120 and the standard deviation is 10. So we know that two standard deviations away, we're going to be at 75%. 3 standard deviations away, we're going to be at 89%. So that's this number here, twice the standard deviation. So 2 times 10 is 20. This is the mean. So the mean minus 2 times 10, so you get 100. And add that, you get 140. And here you subtract 3 standard deviations. And so that's 30 you're subtracting now, so you get 90 and 150. So at least 75% of the data has systolic blood pressures between 100 and 140. That's the 2 standard deviations away. And 3 standard deviations away, we're at 90 and 150. So we're computing, notice the different symbols here. This is the mean minus twice the standard deviation. This is the mean minus twice the standard deviation, and this is the mean minus 3 times the standard deviation. So the different symbols are because this is a sample, not a population. But anyway, they're using Chebychev's inequality. The coefficient of variance is used to compare different data sets that don't have the same units. So it tells how large the standard deviation is relative to the mean. It can be used to compare the spreads of data sets whose values have different units. The coefficient of variance is found by dividing the standard deviation by the mean. So it's just a division problem. National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia, had a mean of 49.8 inches with a standard deviation of 7.6, and the annual temperature had a mean of 62 degrees Fahrenheit with a standard deviation of 1.3. So the reason why we're using the coefficient of variance here is because we're looking at snow, basically, and we're looking at degrees. You can't compare snow with degrees, but if we convert them to the coefficient of variance, we'll be able to compare the spreads. So for the precipitation, you take the standard deviation. Again, it's given to you at 7.6, and you divide it by the mean, which is 49.8. So divide that out, you get 0.15, and the coefficient of variance for the temperature is the standard deviation of 1.3 divided by the mean, which is 62.2, and you get 0.02. So the coefficient of variance for precipitation is larger than the coefficient of temperature. Therefore, the precipitation has a greater spread relative to the mean.